How's it going, ladies and gentlemen? Mr. Donnie here, looking at 9.6 multiple bonds. All right, a typical double bond, blank. So here on the screen, I have a nice image to show a single and a double bond, right? So here we have our single bond, and then up top, we have the second bond, our double, and below, right? So we have in the middle here, the overlap in between the two atoms. Well, that's the sigma bond. And then the above and below it, not directly in between the two atoms, we have the pi bonds. Right? This is one pi bond because it's one p orbital overlapping. Right? Remember the shape of the p orbitals? They kind of look like peanuts. Right? So what's actually happening is these are overlapping above and below it. Those lobes of the one orbital for each atom is overlapping. And we know double bonds are stronger and shorter than a single bond. That is true. Consists of one sigma and one pi bond. That is true. Imparts rigidity to a molecule is true as well. Because we have this overlap above and below it, they can't spin. Normally, if it was just a sigma bond, we had just two atoms connected by the bond in the middle, right? Then these things could spin around and they wouldn't be rigid. They could turn. Right, so this could also spin around just a sigma bond. They could spin, but with the pi bond above and below it, you can't. So it definitely does impart rigidity to a molecule. Consists of two shared electron pairs. Facts. So we have the shared sigma and then the shared pi bonds right there. So that's two shared electron pairs. So all of those things are correct. 21, a typical triple bond. Well, first thing that we're going to get is we're going to get a sigma bond. And then if we have a double bond, so this is one bond. If we have a double bond, it's going to be a sigma plus a pi bond. And then if we have a triple bond, it's going to be a sigma plus two pi bonds. So here we're illustrating one pi bond with above and below, but it could easily have another pi bond come out along the sides as well, just like how it did up top and below. Bond. Choice A. 22. Electrons in blank bonds remain localized between two atoms. Electrons in blank bonds can become delocalized even or between more than two atoms. So sigma bonds are always directly in between two atoms. That's sigma territory. That's what a sigma bond is. So electrons in sigma bonds remain localized between two atoms. So this is definitely going to be sigma. Now, I've found some pictures to show you the p orbitals in benzene, right? Benzene's this ring in two dimensions. We draw its structure like this, and it shows double bond there, but it also has resonance. The double bonds are between the other two carbons. Well, which one is it? It's both. Remember resonance, it's both. It's a hybrid of those. Those electrons don't stay fixed where the drawing says they would be. They don't stay there, they get delocalized. So all these pi orbitals overlap, forming the pi bond, and it forms like a molecular orbital for the whole thing, around the whole molecule, where the electron can go. So this is an image over here. We have those electrons just being delocalized above it, those lobes all kind of bloop together, and below it, all those lobes kind of bloop together like water droplets coming together, no longer localized between two atoms. They can move around the whole molecule. So the second one would be the pi. So sigma and pi. The next question, if you ran into trouble, like, oh wait, nope, not this one, sorry. So there are blank sigma bonds and blank pi bonds in this molecule. And remember that those stupid boxes are supposed to be double bonds, right? So every single bond is a sigma bond, and every double bond is a sigma and a pi. So you're just kind of, it would probably help to draw it out. So when in doubt, draw it out. Double bond here, CH, and then CH2, and then C. Oh, what's going on here? CH. This is a triple bond right here. Stupid boxes, but you should have been able to look like, hey, this carbon only bonded to one hydrogen, so it must have made a triple bond. And this carbon here didn't have anything bonded to it, so it must have had triple bond, single bond. All right, I'll fine, stop yelling, I'll draw the H's. So now it's just going to be a matter of counting how many single bonds there are and then how many double bonds there are. All right, so I'm going to just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 sigma bonds. Now I go back and start counting my multiple bonds, where here's 1, 2 pi bonds, 3 pi bonds. So a total of 3 pi bonds. So choice E. 24. Which of the following molecules or ions will exhibit delocalized bonding? So this one, you might have thought all of them should have been, but I think based on the key, what they were going by was they were using the octet rule. So they were figuring out what the structures were based on everything completing an octet and not having more. So if we take a look at the structure for SO2, well, it's going to have 18 valence electrons. So SO. And it is going to look like this once we get done with making sure everything has satisfied the octet rule. So when we're looking at it this way, yeah, it definitely has resonance. So this one has delocalized bonding because it has resonance. If we take a look at SO3, that's going to have 24 valence electrons. So we draw it, and we place all our lone pairs of electrons around it, but then you go, oh, hey, sulfur doesn't have a complete octet. So what we're going to have to do is we're going to have to make a multiple bond with one of those oxygens so that everything has an octet. Right now I've placed my 24 electrons, everything has 8. Awesome. This also has resonance because you go, oh, hey, wait a minute. That double bond could have been between the other oxygen, or it could have been between the other oxygen. So it has resonance, it'll have delocalized bonding. Now with SO3 minus 2, there are structures that you could draw where it would have resonance, but based on the answer key, I think they're going by making sure the octet rule is satisfied. So you would go, well, how many electrons is that? That's going to be 26 valence electrons. So we put sulfur in the middle, oxygen, 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 complete our octet. And now we've only used 24 of our electrons. Where do the other 2 go? On the sulfur. Now that's why we don't need to make a multiple bond, because sulfur now has 8 valence electrons. So we don't need to show a double bond, which means we wouldn't have a resonance structure. Could you have, Mr. Donnie, wouldn't the formal charges be lower if we did make a multiple bond? Yep, they sure would. And that's why I don't really like this question, because, you know, if they specified, you know, based on the octet rule, I'd be okay with it, but they didn't. So I'm not a huge fan of this question, but that's the answer. C right there. 25, the hybridization of the terminal carbons of C boxes. Yeah, I'm sorry, guys. You would think an equal sign wouldn't be something technology would freak out about. So I would just draw it. Draw it out. And this is what the molecule is going to look like. And now it says, well, what is the hybridization on the terminal carbons, meaning the end carbons, right? Well, they're identical. So let's figure it out. Well, we got 1, 2, 3 different sigma bonds. So remember, when we're doing multiple bonds, a sigma bond is going to be with the hybrid orbitals. And any pi bonds are going to be unhybridized p. That's not how you draw p orbitals. So for everything, every domain that we got, we need a hybrid orbital. So we got 3 domains, so it's going to have to be sp2 hybridization, which is going to be choice B. All right. So what's happening with that carbon is that it's making its sigma bond with a hybrid orbital in between the two atoms, which crudely drawn here. Now for the pi bond, well, that's going to have to be an unhybridized p orbital from the carbons, which I suck at drawing, huh? So they're overlapping above and below it at 1p orbital. So this is what happens, right? We take the one of those s's, and we take two of the three, and we hybridize them together, and we get 3 sp2 orbitals, and we get 1 p orbital that's unhybridized. All right, well, I hope you found that helpful. Bring your questions, ask them, and I'll see you in class.